Okay, grade 11 physics. This is our last unit. It's about electricity and electromagnetics. So I'm basically going to split this into two videos, one about electrical concepts, mostly a grade 9 review, and another one about electromagnetics, which is more about the applications of electricity. So this is the grade 9 electricity review kind of video. Here's what we're going to cover. We're going to talk about conventional current versus electron flow, and then talk about DC versus AC current. We'll talk about the basic electrical concepts of voltage, current, and resistance. We'll talk about Ohm's law and some applications of it in terms of power dissipation in electrical circuits. Then we're going to switch gears into some new stuff and talk about Kirchoff's laws. You might have seen this in grade 9, you might not have. We're going to derive the equation. We use Kirchoff's laws to derive the equations for parallel and series resistors. We're going to use those equations to solve some basic circuit analysis problems. That's what I'm trying to get through today. So the first thing that I want to talk about is conventional current versus electron flow. We now know that electrons are negative. They are negative point particles, and they flow, obviously, from negative to positive. They're going to run away from the negative charge. They're going to get attracted to the positive charge because opposites attract. But back when they were just studying electricity for the first time, they thought that it would flow from positive to negative, like from high to low, like water kind of thing. I believe it was Ben Franklin that was writing this down, and I think it was Ben Franklin's mistake. So from high to low. Yeah, so we've kept that ever since. We've kept the conventional current thing ever since, even though it's wrong, because it would take too long to change everything. But thankfully the math works the same for both, and that's why we haven't changed it. So here you'll see a diagram of direct current versus alternating current, and you'll see that the little particles are moving from positive to negative, even though we know that they actually move from negative to positive. But it doesn't matter because it makes a loop. So that's conventional current versus electron flow. The only time that it really makes a difference is when we talk about electromagnetism. We have two different rules for one or the other. We use the right hand for conventional current and the left hand for electron flow. But when we get to that, which is the next video, we're going to talk about it. Alternating current, which is the current that's, in my house, goes back and forth. So honestly, it doesn't matter at all for alternating current because they're always moving back and forth anyway. Yeah. So that's that. Yeah, and we'll talk about DC versus AC now. So DC is the kind of electricity created by batteries because it's an electrochemical reaction. There's chemicals that want to release electrons and chemicals that want to accept electrons. And so the chemicals that want to release the electrons are on the negative side, and the chemicals that want to accept the electrons are on the positive side. And so the electrons have to flow through this way from negative to positive, backwards from this diagram, because this diagram is showing conventional current. But, really they're going the other way. So that's a battery. It produces direct current. There's no, there's no force that's driving the electrons the other way because it's chemicals. It's chemicals that want to release and want to absorb electrons. The electrons only want to go one way. But the kind of electricity that we have in our walls here is alternating current, which is electrons going back and forth. The reason that we have that type of electricity in our walls is a little bit interesting. We'll get more into it into the next video. But basically it's because alternating current is much easier to change the voltage, and changing the voltage is very useful when we want to transmit it by long distances. So alternating current works better in transformers, and that's why we use it in our houses now. I'm going to set up a little demo of DC versus AC so you can actually physically experience the difference, and it's one that you can actually do at home. So I'm going to pause it and set that up. Okay, so I'm back, and what I've got here is I've got my speakers. These speakers are USB powered, and you see them here up on top. And right now, because they're USB powered, I've connected them to my little USB thingy here. This green thing is just connected to my power bar, and out comes this cable. That cable is attached here to the speakers. So these are connected now to an AC power source. It's being transformed into DC, but they're still electrically connected, coupled to this AC power source. And because they're coupled to the AC power source, something interesting happens when I touch this guy. So this is the thing for the speakers, and hopefully you'll be able to hear it. So let's see if you can hear it. Can you guys hear that? I'm going to bring the microphone closer. Maybe you'll be able to hear it a bit better now, right? There we go. So we're going to... So what you're hearing there is actually the buzz of the alternating current going back and forth and back and forth and back and forth through the wire. And when I touch it, I have, electrons in me, and my electrons are going to also want to go back and forth. But there's a little bit of inertia to my electrons. They resist the change, kind of like a mass resisting a force. The electric field of me is resisting the back and forth of the AC. This is called impedance. It's a concept we don't really talk about in grade 11, but the idea is you can hear that AC buzz. And depending on where I touch it, actually changes a little bit. And if I touch it here, which is the ground, that's the ground, nothing happens. It's only when I touch top. So if you have a USB microphone, USB speakers, you can actually try this yourself, which is kind of fun. But here's the cool part about it. If I instead connect these to my battery, okay, here's just one of those battery packs. You can plug in USB to it, and I plug in the USB to it. Now these speakers are on. You see that they're on. And they're connected to USB, and they're right in front of the microphone. But if I touch it, nothing happens. Nothing happens because this is direct current that's feeding these speakers now. And direct current, you don't get the same kind of impedance. You don't get the same capacitance from your skin. So you don't get the same buzz, even though these speakers are on and connected to a power source. So it's a very kind of in-your-face demonstration of DC versus AC, which is kind of cool. Okay, I'm going to pause again and we'll get to the next topic. Okay, so the next topic is going to be, here, voltage, current, and resistance. Before we get to that, though, I have to talk about the Coulomb very quickly. The Coulomb. It's a number, it's kind of like a mole if you've taken chemistry. A mole is a certain number of atoms or molecules or anything. The Coulomb is also kind of a number. It's a package of electrons. It's the basic unit of charge. It was defined in a certain way back in the day by experiment, but now we know that it's about this many electrons. Specifically that many. It's been internationally defined as exactly that many electrons, and it's the measure of electric charge. We're going to work with coulombs because it's annoying to talk about per electron. We're going to talk about energy per coulomb of electrons. So think about it like a billion or a million. It's like a pack of electrons, basically. So let's talk about the hydrodynamic analogy. Because we talk about electric current, we can make these analogies to water current, and it's kind of how they started understanding electricity. They thought of it as an electrical fluid, electricity juice, and it would flow like a fluid. So that's what they talked about. So battery is the voltage. The voltage is actually defined as how many joules each coulomb of electrons has. So how many joules each coulomb has. Remember, a coulomb is a pack of electrons. It's one of these like bricks of electrons. So In the water analogy, it's how many joules each, I don't know, liter of water has, each pack of water. And you know, this energy is potential. It's a potential energy. So, you know, here's a very tall dam. Here's a very short dam. This is the Chaudière Falls in Ottawa. This is, I believe, the Hoover Dam. And this water, each liter of water is going to fall further than each liter of water here. So this is a high voltage source. This is a low voltage source in our joules and coulombs thing. It's the amount of energy each electron has, well, each pack of electrons has. It says nothing about how fast that energy is being transferred. You can have high power with low voltage. You can have low power with high voltage. That depends on how many gates you have open on your dam, right? It depends on how open your dam is, not how high your dam is, how many gates you have open. So there's a difference. Voltage is not necessarily power. Voltage can contribute to power, but it's not necessarily power. So, you know, here's a 1.5 volt battery and a 9 volt battery. This is low voltage. This is high voltage. It's purely the amount of energy each pack of electrons has, and how much, and also a measure of how much energy they lose in the circuit, how much energy they gain from the battery. Resistance. Resistance is a good one. Resistance in that dam analogy, in that electric dam analogy, would be the water coming in fast but then losing speed as it goes through the turbine. Here, the resistance is a transfer of energy into something else, anything else. So we might think that resistance is bad, but resistance is anything. A light, a motor, some speakers like I had before. Every load on the circuit has some resistance. The wires have some resistance too. And one way to think about it is like a pinching of the water flow. I don't actually like that analogy that much. I like it, think of it more as, you know, stuff that's stuck in the pipe, stuff that's in the way, because in this case, when the flow slows down, it'll speed back up again. But in electrical resistance, they lose energy, and that energy stays lost. So, yeah, it's kind of how much energy, well, not how much energy they lose, but it's how much the current gets impacted by whatever it's passing through. It's a drop in voltage, and I'm going to show off another little example of this over on the side here. So let me pause. Okay, and I'm back, and what I have here is two kinds of steel wool. This is steel wool. One is coarse, one is super fine, and this is what they actually look like here. I'll show you the actual steel wool. This is the coarse, see how it's kind of big, and this is the superfine, which is much finer, and you can see the difference between the two. And this is what it looks like here. Here is a coarse fiber. You can actually see it. There's the coarse fiber. And the superfine is very, very small. It's so small, I have to kind of pull it off of this pack. Right? And if I pull it off here, it's so small that it's very, very, very hard to see. You can maybe just barely see it catching the sun there. There it is. It's very, very small. And what I have here is a multimeter. So I'm going to turn it to ohms, which is a measure of resistance. And I'm going to measure the resistance of this guy. So here's the coarse. This is the coarse one here. And if I measure the resistance, you see we've got about 4 ohms of resistance across that wire. Now a question for you guys. What happens if I bring these probes closer together on the wire? Do you think it'll have more resistance or less resistance? The electricity is going to be flowing a shorter path through that wire. More resistance or less resistance? Let's try it. I'm going to bring it down to about here. Oop, hang on. Let me yeah. Fix that up a little. it's getting kind of weird. Okay, let's try it again. So when they're far apart, about 8 ohms, something like that. 8-10 ohms. When they're closer together-ish, 3 ohms. 3, 4, 6 ohms. But less, a lot less than when I had them far apart. See, when they're far apart, we've got more resistance. It's a little bit awkward because I'm using these guys. So 8, 10 ohms on that guy. Let's try the very, very skinny, so skinny you can barely see it on camera, super fine steel wool. Now the super fine steel wool, like that, 20 ohms, right? 23 ohms, something of the sort, 23 ohms. If I bring it closer together, 8 ohms, right? And if I slowly bring them apart, you'll see the resistance getting bigger and bigger and bigger and bigger and bigger. So the further apart you are, the higher the resistance of the cable. Last piece is this, right? This bunch of it. What happens if I bunch them all together and make a big thick piece of steel wool like that? What do you think will happen to the resistance? Well, there's more kind of cables for it to go through, more paths for it to follow. So what we expect is lower resistance, and that's exactly what we get, right? 0.0, 0.2, 0.3. If I bring it close together, it'll be even smaller. 0. We're getting 0. If I go further apart, a little bit higher resistance, but there's lots of paths. So the thickness of the conductor and the length of the run both change how much resistance is in the wire. This is why you need to choose extension cables carefully. You want really thick extension cables for something like an electric lawnmower, anything that takes a lot of power, like a fridge, stuff like that. But for other things, for small things, you can get away with very short lengths of electric cable. And if you're doing a very long run of cable, you need very, very, very thick cables. Think about like power lines. They're huge because they need a big, thick cable to carry that electricity for less resistance, because resistance is going to make you lose energy along the way. So I'm going to pause. We're going to go back over and talk about the last piece, which is the current. Okay, so current, the current itself. So far we talked about voltage, which is the difference in water levels in our water analogy. It's the potential energy of the electrons, joules per coulomb. We've talked about resistance. I'm going to talk about the unit of resistance in a second. But the last piece is the current. Current for water is maybe liters per second, right? Liters per second. Per second, right? How much amount of water goes by in a second. In electricity, it's the same thing. It's how many electrons are flowing through in a second. Note, it doesn't say how much energy each electron has, just how many goes through in a second. If we go back to this analogy here, this one here, right? This dam might actually have more water flowing through it in 1 second than this dam does. There's no relationship between the two, aside from the fact that more energy might make them move faster, but it does depend on how open the dam is. So that's current. They flow through one in 1 second. How many electrons flow through How many electrons flow through the wire in 1 second? 1 coulomb flowing through in 1 second is 1 ampere. 1 ampere of current, and the unit is A for amps. Volts, 1 joule per coulomb is 1 volt. 1 joule per coulomb is 1 volt. Amps, named after ampere, is amps. I'm going to jump over to, I'm going to talk about Ohm's law, which we're going to go over to the whiteboard in a second. But this was created by this guy, George Ohm, a German he did tests on how resistance affects current. You know, how many electrons are going by in a second, how many volts you needed to push so and so many amps, things like that. And he came up with this law. So we're going to go and talk about this law over on the other thing. So let me just get over there. Okay, so I've got my my whiteboard out, and I'm also going to put up this funny little image, that one there. So here's a cute little image of, down here is a cute little image of the volts, which is the energy. All right, volts is the energy. The amps, which is the current, how many electrons can go through in a second, and the ohm, which is slowing down the current. All right, and that's basically what George Ohm figured out. He worked out that when you increase the voltage, the current, which is I for intensité, because Ampère is a French guy. When you increase the voltage, the current goes up. When you decrease the voltage, the current goes down. This shouldn't be surprising, right? When you raise the level of something and you have more potential energy, things are going to go faster. When you decrease the potential energy, things are going to go slower. And when you raise the resistance, the current goes down because, there's more resistance. And when you lower the resistance, the current goes up. Again, same idea. Well, remember, resistance is how narrow, how much stuff is in the way. So when you lower it, obviously you're going to have a faster current because there's less stuff in the way. And he put this all together. He actually did, a proper study of this. He found out that the voltage is proportional to the current. Voltage is proportional to the current in any system, meaning that twice the voltage gives you twice the current. And he found out that the resistance is proportional to 1 over the current. So twice the resistance is half the current. Stuff like that. And he came up with an equation. And what I like to do is I like to make a reference to F equals ma, right? Force is the force, m is the mass, which resists acceleration, and a is the acceleration itself. He came up with V equals I times R. In this case, V is the voltage, the potential energy. I is the current, almost like the acceleration here, and R is the resistance to current, the resistance to voltage. So V equals IR, a very important equation. This is called Ohm's law. Ohm's law, this guy. You can obviously rearrange it. I becomes V over R. That's actually a better way of saying it because clearly more voltage makes more current, clearly more resistance makes less current. It's probably closer to what Ohm actually figured out. And R, of course, is going to be V over I. So this actually gives us our unit, the unit of the ohm. Remember that we have physical descriptions of the volt. A volt is joules per coulomb, right? It's how much energy each pack of electrons has. And an ampere is coulombs per second, which is again a physical measurement. It's how many electrons are going by in a second. It's like a speed kind of thing. So energy and speed, things that we can physically measure. But the last piece, right, this last piece, resistance, is you can't really physically measure it. You have to measure it by checking the volts and the amps. So the last piece, named of course after ohm, the ohm, an ohm is voltage over current, right? Voltage over current, joules per coulomb per second, which is a little bit of an interesting one because it is joules per coulomb over coulombs per second, which is joule seconds per coulomb squared. All right, a little bit strange. That's resistance, but we just have a symbol for it, which is omega. omega because ohm. I guess O was already taken, so ohm, omega. Yeah. That's resistance. Resistance is the one that is defined by comparing the voltage and the current. The other two have, as I mentioned, physical definitions. This one is a derived quantity. Resistance is a derived quantity. That's that. We're going to pause and move on to the next step. So, pause. Okay, so I'm back off pause. I wanted to talk about one more thing. This is the last part of the intro, the last part of the grade 9 review, and that's power. All right, power. And maybe what I'll do is, power. So not going to do that. Power is, as you remember, is energy, change in energy over change in time. Energy over time, which is joules per second, right? 1 watt is 1 joule per second. 1 joule per second. Well, we can actually get an equation for power from our equations for electricity, right? 1 volt, right, is 1 joule per coulomb, right? The amount of energy per amount of electrons. 1 amp is 1 coulomb per second, and 1 ohm is essentially 1 amp. V equals IR. R equals V over I. Yeah, no, I screwed that one up. 1 volt per amp. 1 volt per amp. If we look at joules per second here, right? Joules per second, joules seconds. This is divided by coulombs. This is times coulombs. So what you can do is you can figure out how many joules per each coulomb and how many coulombs are going by in a second. And you end up with P equals I times V. Let's prove that. P is equal to coulombs per second times joules per coulomb. And the coulombs is going to reduce to 1. So power is joules per second, which is good. That's what we want, right? That's what we have up here. Power is joules per second. So power in watts in an electrical system is joules per second, as amps times volts. If you multiply the amps times the number of volts, you always get the amount of power in watts. And this happens in the battery, it happens in any of the loads, it happens everywhere. Now there's a second one here that you can do. If you start from P equals IV, and you know that V is equal to IR, which is Ohm's law. If you remember, V equals IR is Ohm's law. We just take that and we stick that in there. You have a second equation for power. P equals I times R, right? I times IR, because that came from there. And so power becomes I squared R. P equals I squared R. And this is a really good example. This is a really good equation for, that equation is very good for the power loss through a resistor. Because you don't need to know the voltage. You just need to know the resistance and the current, and it's always going to give you the same power loss, which is kind of cool. I like to think of a resistor as kind of like friction, right? Friction is always slowing you down the same rate no matter how fast you're going. Same thing happening with P equals I squared R. You're losing the same amount of power no matter how much voltage is going through, because voltage is just joules per coulomb. It has nothing to do with how many electrons are going by in a second, and that's where the power loss is actually happening. So, kind of cool. So power loss of a resistor does not depend on voltage. Does not depend on voltage. Right? Does not depend on voltage. It depends on current. And then you're saying, but Mr. B, you just told me with Ohm's law that current depends on voltage. Well, yes, it does. We'll talk about that when we talk about power transmission in the next video. So we're going to go back over to this view here. Here's basically that exact same thing. And these are the two formulas, just in a fancier way of saying it. Yeah, so once again, now I'm going to pause and we're going to go over to circuit analysis. We're talking about Kirchoff's laws and analyze some circuits, and that'll be the end of the video. So going to pause, flip over to another note. Okay, so we're back. We're on the next section. This is going to be about Kirchoff's laws. So we're down here into circuits and Kirchoff's laws. And this is going to be, there's going to be 3 practice problems here, so that's going to take up the bulk of our time. First, let's talk about Kirchoff's laws themselves. Gustav Kirchoff was a German. He was one of the great minds of his time. He did a lot of very, very important contributions to science, including inventing the spectrometer. He had famous students like Mendeleev, who went on to develop the periodic table, and Max Planck was one of his students as well. He went off to start quantum physics, so really a great guy. Sadly, not talked about very often. So Kirchoff, he came up with these rules. This was actually part of a exercise that he did in university, just a seminar exercise in university, and eventually went on to become his PhD thesis, which is pretty cool. He was just kind of working on it as a problem, and it turned out to be the big thing he's known for. So the first rule is fairly straightforward. It's called the junction rule, or the current law. It says that the current going in is equal to the current coming out of any junction. So, basically, it's like a river splitting up or merging, if we use the water analogy. Just note that the water analogy is very handy when we talk about Kirchoff's laws. Here we might have, for example, a current coming in, a current total coming in, I, that's current for current I total coming in. And we'll have the same total current coming out because, where else is that water going to go? IT, total current out. But it splits. It splits into, a left side and a right side. Right, we might call that I1 and I2. I1 and I2. Right, and then they're going to recombine back into IT. So Kirchoff's current law works based off of junctions. The current at any junction coming in, so here, right, here's current coming into a junction. There's IT. It's going to be perfectly split into I1 and I2. So here's, I2, and here's I1. I1. All right, that's I2 in my diagram, I2, and I1. I1. Right, as they split, and then they're going to recombine back to being IT coming out. Right, and it makes sense if you think about it for water. Same thing for electricity, because we have that nice water analogy for electricity. So that's that. So specifically, it says that in a junction. So in a junction. IT into I1 plus I2 plus I3, right, that kind of thing. So here, whatever current flows in is equal to the 3 currents flowing out. Which leads to some interesting things, right? When we have current flowing out of this this battery, right? Current flows out, some amount of current, IT. And if I ask you how much current flows through here or here or here, it's the same current all the way around. Right? It's the same. There's no split in current, depending on how much current. Here there's half an amp, so it's going to be half an amp through this resistor, half an amp through this resistor, and half an amp through this resistor. So that's the first law. It's pretty easy to understand. Kirchoff's second law is a little bit harder to understand. It's the voltage law. Specifically, the voltage law says that any loop from a battery will always have the same total voltage drop. Actually, it's the total voltage drop of any loop is 0. Basically, you can think of this as the battery being like a pump, bringing the water up in energy, and then each resistor, being a loss of energy for these electrons. So energy up, energy down, but because it has to come back to the same terminal, overall you have to have a net 0 of energy in your loop. So that's going to be 0 energy. So whatever energy the battery gains, maybe plus 5 volts, this would have to lose 5 volts together. So maybe, let's actually do something here. Let's say this battery, let's see that battery is plus 5 volts, right? It means that on the way back down, these would have to be this might be minus 2 volts, and this would have to be minus 3 volts, kind of thing, to match back up with 5 volts, because it has to come back to the same place, and you can't just get energy for free, so it just comes back to the same place. And this is true everywhere. Every loop must have this. So we have up by 5 volts here, down by 5 volts, down by 5 volts, that way. Or up by 5 volts here, it has to come down the other way. So whatever loop, this red loop in here, this loop in here, and there's actually another loop here, this loop. Remember, any loop has 0 voltage, so this loop also has 0 voltage, which tells you that V3 must equal V2. That's another thing that Kirchoff's voltage law says, is that V3 must equal to V2. And if we think about why, if we use the water analogy, that makes sense, because it has to, if it's from here to here is a certain energy drop, it'll be the exact same energy drop from here to here. How can it not be? It's in the same place. So that's Kirchoff's loop law, Kirchoff's voltage law. The analogy here is a series of waterfalls. So you might, for example, have a total current, a total voltage drop of, let me change that up. From here to here, that entire drop is going to be the total drop. And you'll have V1, and you have V2. Right? And if you had a V3 here, this guy here, right, another resistance, you know that V2 is equal to V3. It has to be. V2 is equal to V3. And V1 plus V2 has to equal to VT. That's Kirchoff's voltage drop rule, right? This idea that this plus this must equal the total height, which is what the battery is providing, the pump is kind of providing. That's the idea behind Kirchoff's voltage law. So that's the end of Kirchoff's laws. I'm going to pause and we're going to get into some analysis with this. Next up, we're going to use this law to derive the equations for resistances in series and parallel. So I'm going to pause. Okay, so we're into using Kirchoff's laws to derive the resistance formulas, the formulas for total resistance. Here's our keep in mind. In series, current will stay the same, and in parallel, voltage will stay the same. So those are Kirchoff's laws that we just talked about a second ago. The water analogy can help you think about it. So here's a series circuit. What we have is a battery increasing the energy of the electrons, and they fall down 3 resistances, so they're going to lose energy 3 distinct times. This is a series circuit, so we know that the current will stay the same. So I'm going to jump over to the webcam view over here, and what we have is our we have, as I've written that out here, and what we want to do is solve for the current through each current through the whole thing, and then the voltage of each individual resistor. This one is the highest resistance, this one here, the 300, so we expect it to have the most voltage drop, which kind of makes sense, because it's the highest, it's the most energy that's going to get lost. So how do we analyze it? Well, we use Kirchoff's laws. Kirchoff's laws say that in series, the current stays the same. So whatever current is coming through here is also coming through here, is also coming through here, is also coming through here. It's just current all the way through, right? All the currents are all the same. So that tells us that I1, or I battery, is this current, this current, and this current. So I1 equals I2 equals I3 is what we can say, if this is 1, 2, and 3. I1 equals I2 equals I3. And the other thing that we know is, based on Kirchoff's voltage law, is however much this went up by, 9 volts, this must go down by 9 volts, right? Because, because it has to go down by 9 volts. So V1 plus V2 plus V3 has to equal to 9 volts, because they're coming back to the same place and then going up by 9 volts. So with that together, we can work out how much current is going through the circuit, because V equals IR. There's Ohm's law, V equals IR. And I then is equal to V over R. So far so good. Hope so. And I1 equals I2 equals I3, which means that V1 over R1 equals V2 over R2 equals V3 over R3. Hopefully we're on the same page. From there, we can work it out. Actually, I think I've got this a little bit backwards. I'm going to pause and think it through just a sec. Okay, so I unpaused. I paused and I thought about it for a second, and I realized it's easier to actually, instead of using that, we use this guy, V equals IR, because that means that I1 times R1 plus I2 times R2 plus I3 times R3 is going to be 9 volts, right? It's 9 volts, because 9 volts, and V equals IR. V equals IR. But we know that this I is the same for all of them, so I don't want to just call it I. I times R1 plus I times R2 plus I times R3 is equal to 9 volts. Which, if we collect our terms, means that I times R1 plus R2 plus R3 is equal to 9 volts. When we can rearrange now and get rid of the I, is R1 plus R2 plus R3 is equal to 9 volts over I. 9 volts over I. Which, 9 volts over I, that's voltage over current, which is the resistance, the total resistance of the circuit. So this is where we get our resistance right? R1 plus R2 plus R3 is equal to the total resistance of the circuit. But that's, that's not fully where we're going. We want to know the current through this whole thing, because if we know the current through this whole, through this guy, we know the current here, here, and here. We can figure out the voltage there, there, and there. So, we can flip these, so I then becomes 9 volts over R1 plus R2 plus R3, which is the total resistance. So that's the current that's going to be going through the battery. We're solving for this current here going through the battery. Well, indeed, the current going through the entire circuit. So that's 9 volts over, and we have 100, 30, and 50. About 350 ohms, which is 9 volts over 450 ohms, which is 0.02. That seems reasonable, yeah, 0.02 amps. 0.02 amps. If I double check that, 9 divided by 450, yeah, 0.02 amps. Yeah, so that's how you solve it, and we came out with an important equation here, which is that in series, right, in series, the total resistance is R1 plus R2 plus R3, right, 0.02 amps. And then we can use that to solve for each individual one. We know that the current now is 0.02 amps. We know that current, so we can solve for the individual voltages. Right here, V equals IR. 0.02 amps times 100 is 2 volts. Here, V equals IR. 0.02 amps times 300, that's 6 volts. Right? And here, 2 volts, 6 volts, the total is 9. We could actually just work out that this is going to be 1 volt. And just as we predicted, this guy has the highest voltage because it's got the highest resistance for the same current because of V equals IR. Yeah. Okay, so that's the first example. We're going to move over to, I'm going to move over to the second example, which is over here, right, in a parallel circuit. And in a parallel circuit, we're going to try to do the same analysis, but just like this, which I'm going to pause and set it up, and we'll get back to it. So, okay, so we're in parallel now. And here's the setup. We have 9 volts, 90 ohms, 45 ohms, and 180 ohms. And in this case, the current is actually going to split. Right? The total current is going to split into a 1, a 2, and a 3, and then they're going to all come back together. Right? I back to IT, but this is I1, I2, and I3. Right? The current is going to split, but in parallel, voltage stays the same. That is Kirchoff's voltage law. So what Kirchoff's voltage law does, and this is a little bit counterintuitive, is because this went up by 9, this must come down by 9. Right? And this is also 9 volts, and this is also 9 volts, because an electron going through any one of these branches is always coming back to the negative terminal of the battery, so it's going to have to lose 9 volts of energy along the way. Well, 9 volts of potential, I can't say energy. Each coulomb will lose 9 joules coming through this circuit. So we know that it's always 9 volts, 9 volts, 9 volts, and we have the resistances. So we'd actually figure out the currents straight up from V equals IR. Right? V1 equals I1 times R1. We know V and we know R. We just solve for I. I equals V over R. I equals V over R. So, we know it's 9 volts. We know R is 90 ohms. That means there's 0.1 amps coming through I1. I2, right, is 0.1 amps. That's over 0.1 amps. 0.1 amps. I2, same idea, V1, V2 over R2, which is the same 9 volts, right? Same 9 volts because of the loop law, over 45 ohms. Means there's more current going through the smaller resistance, which makes sense. It's a smaller resistance. It should have more current. So that's 0.2 amps. And then the 180 I3 is going to be V3 over R3, which is the same 9 volts over 180 ohms, which is 0.05 amps. 0.05 amps. Okay. And then to figure out the total current, you just use the junction law. They come together, 1, 2, and 3, all have to come together for IT. So IT is going to be 0.1 plus 0.2 plus 0.05, which is 0.35 amps coming through here, because the 3 currents all come together. So that one's pretty straightforward. You actually can figure it out pretty easily. The neat thing, you can use it to work out the total resistance, right? Total resistance. What is our total resistance? How many ohms? Well, V equals IR, so R is V over I. We have the total current, right? I is I1 plus I2 plus I3, which is 0.35. So here R is going to be, RT total is going to be our 9 volts over 0.35 amps. And our total resistance is going to be, let me just grab a calculator real quick, 9 divided by 0.35, 25.7 ohms. 25.7 ohms. Right? It's actually less resistance than any one of these. Because we're basically, the reason that it's less resistive than any one of these, this is a little bit counterintuitive, is we're adding more paths. Adding more paths for the electricity to go. So this 45 slows it down a certain amount, but then it's got other ways that it can go, so it's going to end up going faster overall because we're giving it extra places to go. So in this case, adding resistors actually makes the total flow faster because we're giving the electricity more chances. It's like when I braided my little piece of steel wool earlier in the video and I gave it more options to go, right? Each individual one still has the same resistance, but together they have less resistance. Yeah. This leads us to the total resistance formula, right? RT is the voltage over the current. But if we look at the current here, which is total voltage over I1 plus I2 plus I3, right? That becomes VT divided by these guys, right? V1 over R1 plus V2 over R2 plus V3 over R3. Right? That's so far, except each of these is the same V. Right? It's just VT the whole time. It's voltage, it's 9 volts. 9 volts, 9 volts, 9 volts. So it's just VT the whole time. So what you end up with then is VT over VT times 1 over R1 plus 1 over R2 plus 1 over R3. Kind of in an interesting way. And that's equal to RT. This is an interesting R1, R2, R3. It's interesting setup because what we end up with is when we cancel this out, this becomes 1 and 1. RT becomes 1 over R1 plus 1 over R2 plus 1 over R3. But it's easier stated as, if we flip both fractions, 1 over RT is 1 over R1 plus 1 over R2 plus 1 over R3, and so on. So that's in parallel. That's how you work out the total resistance in parallel. It's a very important equation. You have this on your cheat sheet though. So that's how we figure it out using Kirchoff's laws. Yeah, that is a long video, so I'm going to stop it there, and I'm going to solve some practice problems in the next video for you guys. But that's your basics of Kirchoff's laws and your basics of electrical circuits. Yeah, thanks.